Okay, welcome back to The Explainer. When you see a massive car crash or fireworks exploding in the sky, or even just a messy break in a game of pool, it looks completely chaotic, right? You'd think calculating where all those flying pieces end up is basically impossible. But here's the secret. Physicists actually don't sit around calculating every single messy detail of an impact. Nope. They use a specific set of shortcuts. You can think of them as the literal cheat codes of the universe. Today, we're going to decode how the fundamental laws of conservation let us totally skip the chaos of a collision and perfectly predict the aftermath. And actually, to prove just how absolute these laws really are, we're going to start with a literal life-or-death scenario.
So, would you bet your own life on a math equation? I mean, it sounds like some crazy philosophical hypothetical. But for MIT professor Walter Lewin, it was a practical demonstration. To show his absolute, unwavering trust in the physics principles we're talking about today, he performed this incredibly famous, totally terrifying experiment. Picture this, okay? He stands with his back flat against a wall in his lecture hall. He takes this massive pendulum bob, literally a wrecking ball, weighing 15.5 kilograms, swinging on a 5.21 meter steel cable, and he holds it just millimeters from his chin. He asks the audience to be dead silent, and then, with absolutely zero initial push, he just lets it go. This massive weight swings all the way across the room, hits its peak, and comes hurtling right back, directly toward his face. And it stops, a fraction of a millimeter from his chin, exactly where it started. The guy doesn't even flinch. As he famously said, and this actually made quote of the day in the New York Times, "Physics works and I am still alive." But, why didn't it crush his skull? How could he be so incredibly certain? Well, he survived because of the conservation of mechanical energy. It's all about the interplay between two forms of energy here. When Lewin is holding that heavy bob right at his chin, it has maximum potential energy. That's energy of position, and zero kinetic energy, because, well, it's not moving yet. When he lets it drop, gravity pulls it down, and all that potential energy converts entirely into kinetic energy, the energy of motion. Then, as it swings back up towards his face, that kinetic energy converts right back into potential. The absolutely unbreakable rule here is that if you don't add new energy to the system, that pendulum can never ever swing higher than its release point. The math literally forbids it. So the big takeaway is that conservation laws aren't just tedious textbook equations. They are the ultimate physics hack. When objects crash into each other, the forces involved during that split-second impact are chaotic. They are wildly complex. Materials compress, they deform, sound waves blast out. Mapping all that perfectly is a nightmare. But conservation laws, they tell us we don't even need to care about that messy middle part. We just look at the total energy and momentum right before the crash, and we know for a fact it must perfectly dictate the state right after the crash. And that beautifully sets up our next tool, the conservation of momentum. So momentum, which physicists write as the Greek letter rho or just simply p, is a vector quantity. That means it has both a size and a specific direction. It's literally just an object's mass multiplied by its velocity. The golden rule here, straight from Newton's third law, is that if no external forces like friction are messing with our isolated system, the total momentum before a collision will exactly equal the total momentum after. It is beautifully constant. You see this all the time in practical lab demonstrations, like with air tracks, which basically eliminate friction so you get this incredibly clean transfer of momentum. Section 1. Types of collisions. Elastic versus inelastic. All right. Let's compare them. On the left side here, we've got perfectly elastic collisions. Think of two incredibly hard billiard balls cracking together. In a truly elastic collision, both momentum and kinetic energy are perfectly conserved. Nothing is lost. Now, on the right side, we have inelastic collisions. And let's be real, in the real world, pretty much all collisions are inelastic. Momentum is still perfectly conserved. Remember, that never changes. But kinetic energy, not so much. Some of that motion energy permanently leaks out into the environment as heat or sound, or just physically deforming the objects, like the crumple zone of a car. Then there's the extreme version, perfectly inelastic collisions. This happens when two objects smash together and actually stick, moving forward as one single combined mass. A really classic example of this is a ballistic pendulum, where you fire a bullet straight into a block of wood. The bullet embeds itself and the whole chunk swings up together. Now, even though a massive amount of kinetic energy gets lost to destroying the wood, our momentum cheat code still works flawlessly. We literally just add the two masses together in our final equation and boom, we can predict exactly how fast that new combined block is going to move. Section 2. Cracking 2D collisions. Okay, so how do we tame the chaos of 2D? When something moving along the x-axis hits another object a little off-center, they scatter everywhere, right? To solve this, physicists use an absolutely brilliant trick. They treat the horizontal x-axis and the vertical y-axis like they are entirely separate universes. Momentum is conserved in the x direction completely independently of what's happening in the y direction.
So here is your exact playbook drawn right from our source materials for solving literally any 2D crash. First up, always draw a before and after diagram. Being able to visualize those vectors is half the battle. Second, set up a table and break the velocities down into their x and y components using some basic trigonometry. And third, write two totally separate momentum equations, one for all the horizontal movement and one for all the vertical movement. Just by doing that, you've taken one totally overwhelming 2D problem and turned it into two extremely simple 1D problems.
But hey, I need to give you a massive warning right here. Do not ever, and I mean ever, make the mistake of breaking kinetic energy into x and y equations. Momentum is a vector. It cares about direction. But energy is a scalar. It only has a magnitude and amount. An object just has energy. It doesn't have up energy or left energy, right? So if you're trying to figure out if a 2D collision is elastic, you simply look at the total kinetic energy before and after, totally ignoring the direction.
Let's apply this to something a little more extreme. Imagine an exploding hockey puck sliding perfectly on completely frictionless ice. This is actually a great problem detailed in our MIT sources. Suddenly, the puck detonates. It splits into pieces, flying off at all sorts of crazy angles. Now, at first glance, this seems like it breaks all the rules, right? Because the explosion adds a ton of chemical energy into the system. The kinetic energy absolutely skyrockets. But remember our cheat code. Because the ice is frictionless and no outside force pushed the puck, the total momentum remains perfectly conserved. If you meticulously map the momentum of all that flying shrapnel on the x and y axes, it will perfectly equal the momentum of the single puck right before it blew up.
Section 3. The ultimate shortcut. Reference frames.
Normally, we calculate a collision from what's called the lab frame. That's just you standing still in the laboratory, watching two carts speed toward each other on an air track. Both objects have different speeds, and honestly, the math can get a bit clunky. But what if you shifted your perspective? What if you virtually rode along with the exact center of the entire system? This is what we call the center of mass frame, and it is a total game changer for scattering and collision calculations.
Now, to find that magic point to ride along with, we calculate the center of mass by taking a weighted average of all the masses and exactly where they are in the x and y coordinates. If one object is way heavier, obviously the center of mass is going to be closer to it. Once you find the speed of this invisible center point, you just subtract that speed from every object in your system. Bam, you've entered the center of mass frame.
And when you do that, pure magic happens. In the center of mass frame, because you are moving perfectly in sync with the average momentum of the system, the total momentum of the system relative to you is exactly 0. It's incredible. Before the crash, the objects appear to just be moving directly toward you with equal and opposite momenta. And if the collision happens to be elastic, they literally just bounce off each other and reverse their directions by exactly 180 degrees. What was a total multivariable algebraic nightmare in the lab frame turns into a perfectly symmetrical, visually intuitive bounce. So look at what we've covered today. We went from trusting our lives to the conservation of mechanical energy with a 15-kilogram wrecking ball to slicing up messy 2D crashes into really simple x and y vectors. And finally, shifting our entire reality into the center of mass frame to turn brutal algebra into just a simple bounce. These aren't just dry equations on a chalkboard, you guys. They are the immutable, unbreakable rules that dictate literally every single movement in the physical world. So next time you see objects collide, whether it's on a pool table or in a car crash, ask yourself, are you ready to look right past the chaos of the impact and see the perfectly predictable mathematics underneath?